All right, welcome everyone to this week's Autonomy Talk. This week is a pleasure to have my friend and colleague Matthew Hale, who is an associate professor of electrical and computer engineering at the Georgia Institute of Technology. So I will give a brief overview of what Matt does, although he's doing a lot of things. So it's going to be a short one. But it's so first of all, he received his bachelor's from the University of Pennsylvania and then MS and PhD from Georgia Tech. And his research group is broadly focused on analysis of flow of information in autonomous systems. And recently he's been very interested in privacy, optimality, and compositionality in autonomy, with special focus on robotics. The compositionality aspect of his work is where we met. Essentially, it's a small niche of people working on compositional optimization. He has been receiving a lot of awards, very impressive list of awards for his work. And today he's going to present this work on compositional tame optimization, which is very intriguing. And so he agreed to receive questions during the talk. So feel free to write in the chat or to directly ask. And without further ado, Matt, thanks again for coming. And I look forward to hearing more about this.
Yeah, wonderful. Thanks so much for the invite. Really happy to be here. Really happy to talk about this. As Joelle said, there is this niche of us who are interested in things like this, and I think we expand that niche by giving talks, helping to broadcast all this. So I'm happy to contribute to that in some small way. So, okay, the title of the talk is Compositional Tame Optimization, and it's 3 words long, and it's going to take us 45 minutes to unpack what those 3 words mean. I'll pick out 2 of those words right now. Tame optimization is not a term I came up with. I wish I did. Someone else got there first. There are some survey papers, interesting work in this area. We'll dig into what that means. Already on the title slide, I just want to say, in the context of this talk, tame optimization is not what's being claimed as new, but compositional tame optimization is. And let's advance the slide. Good. Before I dig in, let me move this. I have this. How do I hide this Zoom title bar? I suppose I should have done this before, huh?
We don't see it though, right?
Oh,
so
if
it's
you
an
don't
issue
see
maybe
it,
to you, but we don't see it.
I'll just live. Wonderful. Okay. So before I dive in, I do want to say everything in this talk is joint work with the 3 people shown here. Hans Rees is a research scientist with me here at Georgia Tech. I was told he gave an Autonomy Talks seminar already. Please be working with him. Also joint with Tyler Hanks and James Fairbanks at the University of Florida. Tyler's a PhD student. James is his advisor. I think James will be giving a talk as part of this series coming up soon as well. So you're hearing from each of us individually, but today, as I speak as well, you're kind of hearing from all of us at the same time. Good. So to just jump right in, what motivates me about this, what motivates me to study compositionality in some of these settings, is the fact that our decision problems often have some form of temporal coupling. And I just want to pick out 3 examples here on the slide to set the stage for this. So example number 1 is state space control. So here I've written out an optimal control problem for a state space control system in a relatively standard form, right? I want to minimize over my sequence of inputs. What I'm minimizing is the sum of these stage costs given by script L. And then this temporal coupling here comes through these dynamics, right? So I have xt plus 1 is f of xt comma ut. And you can see how a decision I make now affects my next state, that affects my next decision, affects my next state, on and on and on and on. You can sort of propagate that across time. Another example is example 2 given here, which comes from Markov decision processes. Now, here there is a stochastic element, right? There's some randomness built in, but in the end, the actions that I take affect subsequent states. Those affect which actions are available and future constraints and things like that. So for example, if my robot is moving in this grid on the left, if it ends up in that letter A state in the upper left, then it can no longer go further up or further left, right? So my previous decision to get there has constrained what I'm capable of doing next. And finally, for the last example, various classes of games. We have a matrix game here. When I think of things like repeated games, what I do now affects the response from someone else, which affects how I will respond after that, and on and on and on and on. So there is this sort of clear theme here, right? Our decision systems have this influence over time. Things like this have, of course, been observed before, but today we're going to make it compositional. And in fact, to ground it, we're going to focus on problems like this optimal control problem up at the top. Everything I present will apply to the rest of this. The top case, the optimal control case, has been our main motivation so far. So that'll be what I present today because it is the most worked out. And in particular, when we think about optimal control here, we're going to adopt what is a pretty common modern approach, which is model predictive control, right? So MPC at this point has been used in industry for decades, really. It's been a mainstay of the research community for quite a while, still under active study, popular, widely used technique. It's a good candidate for us to want to analyze. And of course, what we're going to do here is look at it in its standard kind of typical form, right? Where shown in that diagram there, if right now is time t, I'm going to look ahead some number of time steps. I've drawn it there for 4. I plan my optimal inputs over that horizon. I apply the first one of them. I get to a new state, look ahead again, find more inputs, apply the first of them, on and on and on. We write that out with the math given here in the middle. So what we're doing is saying if it's currently time t, I will look ahead to say time t plus n, and I will minimize my costs, the sum of my L's over that time horizon. I have my dynamics, xk plus 1 is fxk plus uk, and then we allow these inequality constraints as well, right? So g of my current state and my current input must be less than or equal to 0. This encodes pathwise constraints, things that must hold at every time, things like that. And again, what I would like to do is refine ever so slightly the observation from the previous slide, which is that a decision that I take now parameterizes my constraints at the next time. I want to dig into this. It's a simple observation. It holds immense power for what we're going to do here today. So once I find my optimal input that I'm going to use right now, let's call it u star of k. Once that's computed and applied, I get this next state. So xk plus 1 is f of xk u star of k. Fine. I can do that again, going to the next time step to get xk plus 2. And all I want to say for now is I can nest that expression for xk plus 1 here. So in the bottom line of math on the screen, where there should be xk plus 1, I've put f of xk comma u star of k. Not a new observation, not even that deep. This is a relatively humble observation for us. Here on slide 2, I'm bringing this up so that later on slide 13, I can call back to this and say, well, we must have gotten it right because we've gotten the right sort of nesting compositional property here. So when I refer back to the humble observation, I'm referring back to this. So we're going to study these optimization problems that we have, study their compositional nature. And up front, I want to highlight what it says there in red. These can be non-convex for nonlinear systems. And in fact, we should say that much more confidently, that unless we are extraordinarily lucky, these will be non-convex optimization problems for nonlinear systems. So there's some compositional flavor here in the sense that our inputs, I think of them as having sort of long shadows that last over time. They sort of have these echoes that last over time. And we know we have some optimization problems here in our optimal control problem. We know they can be messy, they can be non-convex. The question is, what do we do with all this? How do we put these pieces together? And in particular, how can we model this compositional temporal coupling that is inherent to our MPC problems while we account for all these different factors I just named? So that's the question for this talk. We're gonna work towards an answer here. As for a starting point, the starting point comes from a perhaps surprising place. I want to dig into some very classic literature for about 2 slides and show that we can use this, but it's going to take some major changes to use it. So first things first, before we dig into that classic literature, we're going to use category theory. It had the word compositional. The talk had the word compositional in the title. Which, okay, kind of hints at category theory. And a fair question is, why might we do that? Why might we use category theory to do all this modeling? These days, there's increased interest in this. There are a handful of voices, I think, making the right kind of noise about this. Just to add my voice to that group, I'm gonna make a few points for why category theory. So number one, it is a natural language for composition, right? When we talk about composing decisions over time, something that's compositional. Oh, Joelle made a bunch of hearts. Okay. Yes. Why category theory? Good. Joelle is happy. Category theory is a natural language for composition, right? So when we talk about composing many decisions, the question actually is not why category theory, but why not, right? If category theory is meant to compose many things, we ought to be using it. It's built for this. Second is that abstraction can offer new insights and new extensions. Depending on who you ask, that is either obvious or highly controversial. But the point I just want to make here is by generalizing our models, generalizing our algorithms, generalizing our analyses, we can perhaps see further nearly for free. By being willing to generalize, we can say our results reach even further than we thought they did. And then third, category theory offers an ecosystem to plug into. So if you state your problem in the language of category theory, what you end up doing is not just making a new model of your problem, but unlocking a huge collection of formalisms that you can use, right? I'm coming at this from a control perspective. So to me, some of these other categories I care about are the categories of dynamical systems, graphs, manifolds, various other things. Alongside that, there is a huge software ecosystem that we can plug into as well. For me, that connects primarily to the Julia programming language, but there are others that we care about. And so basically, by using category theory, you open the door to many other big, new, interesting things. It's seemingly a natural model for this. And so the question is, how do we use it, right? To answer that, the question is, well, what does it take to make a category? And the actual definition of a category is almost deceptively minimal. It's quite easy to make a category in some ways, right? So to at least define a category, we really just need three different mathematical components. So number one, we need objects of some kind. Number two, we need morphisms that map between those objects. And three, we need a way to compose those morphisms. So for example, in the category set, our objects are sets, and then our morphisms are functions. In particular, they're total functions. These are functions that have to be defined everywhere in their domain. So for example, the logarithm, we often think of its domain as the real numbers. It's not a total function because it's not defined on every real. The long and short of it is you have sets, you have functions that are defined everywhere they need to be, and then you can draw diagrams like this, where I can use f to map from x to y, I can use g to map from y to z, or I can compose these and go directly from x to z as well. That diagram commutes. This is sort of this nice formalism we like to see in the category theory context. So we want to have an endpoint that looks something like that for these kind of MPC flavored optimal control problems. And as I alluded to a few minutes ago, we are going to start by looking at some classic literature in order to get there, kind of from a surprising place. So what we're going to do is go back to 1970. This is Rockefeller's classic book on convex analysis. So he was focused on convex problems. I mentioned non-convexity before. I wasn't lying. We're going to get back to non-convexity in a moment. For now, though, let's see what we can take from this classic work. And here's what we're going to do. If we have this optimization problem on the left, minimize f of x subject to g of x less than or equal to 0, h of x equals 0, right? Nice standard form of the optimization problem. We're going to generalize this by parameterizing it. So now minimize f of x subject to g of x less than or equal to y1, some vector y1, vector of parameters, and h of x equals y2. This again is a vector of parameters. As an idea, this is kind of simple. We've essentially added indicator functions to encapsulate our problem. To unpack that a little, we form this y that is y1 stacked up with y2. So y without a subscript is just a big vector of parameters. And we use that to form this bi function, b of x comma y. This is where those indicator functions come in. If you plug in a y, a collection of parameters for your constraints, and then you plug in an x, if x is feasible for those parameterized constraints, the output is just your cost. If you plug in something that's infeasible, the output is infinity. So instead of being on the left where we say, you're over this domain, you're only defined here, here's your objective, we're now on the right saying, well, you're defined everywhere, but if you're infeasible, you get infinity. So far, this resembles things that have been done in the literature before. Rockefeller's insight that got my attention, or I should say our attention, the whole team of us, was this. These bifunctions have an associative composition law, right? And when you think associative composition, this is the sort of thing we like in our categories. So to unpack this associative composition law is called inf multiplication. It's similar to the notion of inf convolution in vector spaces, but it's a little different. And it goes like this. So B1 composed with B2 evaluated at the point xz is just what's on the right. I have b1 of xy plus b2 of yz, and I inf over the y, right? So that middle shared variable, I take the inf over that. This lets us compose bifunctions. Therefore, it lets us compose optimization problems. It's associative. So this puts us on pretty firm footing, right? A pretty good start to building a category. So we can flesh that out. The title of this slide gives it away. Major changes are required to make this useful to us. Pretend you haven't seen that yet. So if we keep going, if we want to build a category, by the way, Rockefeller left it here. So this categorical stuff, this is us. This is new. We can take objects as our Euclidean spaces like Rm and Rn. We can think of a morphism as a bifunction that maps between these spaces. Composition is precisely that inf multiplication that we had before. We get a nice commutative diagram like this on the right. It resembles the one from a couple slides ago. So far, so good. This looks right. You can make a category out of this. We did that. We use that for linear MPC problems. I just want to point out in this context, when we have nonlinear systems, non-convexity, we will not be able to use this exact form of inf multiplication for composition. We can't use this in its current form as written because it's not a good fit for the class of problems that we care about. The reason I say that inf right there, that's a global infimum. You are finding the global inf of b1 plus b2 over all points y. We care about non-convex problems, and non-convex problems are almost always solved to local optimality. Sometimes you get lucky and you get the global optimum. Sometimes you get really lucky and you have a non-convex function with really nice special properties. In general, though, you might have a function that looks like this. Getting to the global minimum of that is not really something that's done. There are major theoretical obstructions to doing that. In practice, when people do things like training a neural network, numerically solving really messy optimal control problems, you get to a local min and you kind of do your best. Tends to work well. So we will model that here, and we are extra motivated to model it because ultimately it's what people are doing in practice. And so if local optimality is what we get in our non-convex problems, we do need to model local optimality in a composition law. So what's here on the slide now is basically saying the quiet part out loud for how we tend to solve our optimization problems, right? So for some reasonable f, g, and h, more unreasonable in a moment, for some reasonable cost and constraints, we want to do this. We want to locally minimize f of x, starting from some initial condition x naught, subject to h of x equals 0, and g of x is less than or equal to 0. And in this, we want local optimality and we want feasibility. Right? So get to a local min, obey all your constraints. We've got the words in red saying the part that is usually left implicit. So this is what we'd like to solve. Before we can do that, we need to decide what we mean by a reasonable optimization problem, right? What is the class of optimization problems that we're willing to model here? And there's sort of this tension, of course, in this context where we're striving for generality. Alongside that, we need it to be tractable, right? Certainly f, g, and h need to be measurable. Beyond that, okay, what other properties do we want? This is where the tame optimization aspect of this comes in. So a problem is tame if its objective function f and its constraint functions g and f are tame functions. So a tame optimization problem is made up of tame objects. A function is tame if it is definable in an O minimal structure. Okay, so we're going to step through this in a moment. High level, before we do that, I just want to say, in certain areas of math, like model theory, O-minimal structures are the principal objects of study. Those are the main focus of what people care about. This is what they study day in and day out. For us, we're not necessarily going to study this itself. What we're doing, though, is defining the sandbox we're going to be playing in, right? We're defining the boundaries of what we're willing to consider. So we can think of this as setting the stage for how we will be able to define problems coming up. As for what an O-minimal structure is, we mostly use the typical definition. So first things first, number one, an O-minimal structure is the sequence made up of the S sub n's. Each S sub n needs to be a Boolean algebra of subsets of Rn. So I need to be able to take unions, intersections, complements, things like that. Second, if I've got two things that are defined in some part of the sequence, their Cartesian product also needs to be definable in my O-minimal structure. Third, if I have this projection map where I chop off the last coordinate of, say, every vector in a set, the set A, that projection where I chop off that last coordinate, that projection needs to be definable in my O-minimal structure. And then finally, this last set, this tuple x1 through xn, where that first and last coordinate are the same, that must also be definable here. One more thought on that, then we'll talk about really what we're doing with this. This fifth point is often not stated, but we need it. So S0 must be R0, where R0 consists only of the origin. If that feels trivial, it is. Under the hood, this helps us make a category theory. You know, I enjoy working on this stuff because it makes you get your ducks in a row. Turns out getting your ducks in a row means appending this trivial but ultimately consequential statement. So we have that there. All right. O-minimal structure, we've defined it. The real point behind this, the real reason this is here, is that it will help us define reasonable optimization problems, right? So we can have structures that look like these, feasible regions that look like these. weird spheres, cylinders, interesting algebraic surfaces, things like that. And when I say algebraic surface, I'm kind of hinting at something bigger. So by working in this O-minimal structure, by working with tame problems where everything is definable in an O-minimal structure, we're including huge classes of functions. So you can define semi-algebraic functions over an appropriate O-minimal structure, analytic functions, sub-analytic, semi-analytic, and many more. You can kind of grow this and expand this. Going forward, in my head, I tend to think of everything we use as being analytic. You can think of these as being analytic functions. Those are sufficiently well behaved for us to be able to work with them. But basically, going forward, when I say tame, tame means definable in one of these structures. This is a way of excluding certain pathologies that we really can't work with while still including broad ranges of functions, right? Saying functions need to be analytic in engineering is not a particularly heavy assumption, so it's something we will proceed with. So we've defined the word tame from the title. A tame optimization problem is one that can be defined here. So let's get back to this, right? We want to solve problems of this form, locally minimize f, subject to all those constraints. We've got a big, gnarly non-convex function like the one on the right. And we know that as we optimize, we're starting from x naught, right? This initial condition x naught. Now, this forces us to confront another question. If you're solving a convex optimization problem, every local min is a global min. They all give you the same cost. That's not true in a non-convex problem. Moreover, depending upon where I start, different algorithms may take me to different local minima, right? So for this plot on the right, you could picture placing an initial condition on the tops of one of those sort of mountains or in the valleys or something like that. Different algorithms can take the same point to different local minima. So the question is, well, where do we end up? Now, this was a critical point in this work where we had to make a decision, what algorithm do we want to use? And the answer is actually, we're not going to pick a single algorithm. Again, we want to model how these things are used in practice, how MPC is used in practice by engineers. And so instead of committing to one algorithm, we're just going to define a certain mapping A, that cal A on the screen. And we're going to say that cal A must have certain properties. So first, it must be tame. It must be definable in our O-minimal structure. Again, this allows things like analytic mappings, not too strong, but we need to enforce our assumptions. And then we would like these algorithms to, so taking a step back, think of an algorithm as a vector field, right? It's nearly a dynamical system. This algorithm must produce flows that keep my feasible region forward invariant. The reason for saying that is really the second bullet there. These algorithms are tame vector fields where they induce flows that I can take the limit of. So I can take limits as t goes to infinity and things like that. I can take the limit as t goes to infinity without becoming infeasible. As for why we choose to model our algorithms this way, this model allows for quite a few different algorithms, or it is a representation of a few different algorithms in the literature, right? So number one would be something like projected gradient descent, where I take a step, I project onto my feasible region, take another step, project again, and on and on. This model also allows for, say, barrier methods, where I add things like the logs of certain constraints so that my cost would go to infinity if I were to become infeasible. It can also model primal dual algorithms when initialized in certain ways, and a lot more. So again, we are modeling model predictive control. Here we are modeling the algorithms we use to solve the resulting optimization problems. Okay. So the long and short of it is, an algorithm A gives us flows. It's a vector field that defines flows, where those flows map initial conditions to fixed points, right? To some solution. Under reasonable conditions, we can say, except for rare pathologies, those fixed points that we end up at will be local minima. So it's fair to say, roughly, an optimization algorithm maps initial conditions to local minima. We do, in that context, in order to model this, need to examine exactly how that happens, right? So how does it occur that the algorithm takes me from some point to some local minimum? Okay, for this, we need to unpack a few things. So we're going to use script F to define our feasible region. This is all the points that obey all my constraints. And then we're going to define the set of fixed points of my algorithm, right? These are all the points that my algorithm may make me end up at. We're going to say that set of fixed points is finite. So a couple things here. One, really I should keep writing A with that bracket FGH. We're just going to call it the fixed points of A. FGH are implicit, but yes, the fixed points depend on the problem. The other thing I want to say here is we're just stating the assumption as saying the set of fixed points is finite. There are various other sufficient conditions we could come up with that imply this. This is enough for our purposes. We will go with this. In terms of these fixed points then, what we're going to define is what in some cases is called the stable foliation of our feasible region with respect to this vector field A. Here's how this goes. So we're going to consider, I'm in definition 3 here, we're going to consider the set of fixed points, P1 through Pn. It's finite because we just assumed it is. Again, not a crazy assumption. And then what we will say is, well, if I optimize from any given initial condition, right, I will follow some flow induced by my optimization algorithm. That flow has to end up somewhere, right? These algorithms are dissipative, so they have limits. I have to end up somewhere. And if you take that statement and make it a little more mathematical, what we're really saying is every point that you could start from is in the stable manifold of some fixed point. No matter where you start, you end up somewhere. So what we can do is take this script f and say, well, this script f is in fact the union of all the stable manifolds of all the fixed points of my algorithm, right? Anywhere you start, you got to end up somewhere. Take all the places you could end up, take the unions of all the places that lead to them. That is in fact equal to the feasible region. And there's a visual I have in mind for this that I just want to talk about here, right? So in the bottom left, we have this nice function, clearly non-convex. It's got 3 local minima, 2 local maxima. And for each of those fixed points, we could ask, where could I start to end up at the green point or the blue point or the red one? And in this case, it's not too bad, right? So if I take the black line, the sort of x-axis as my feasible region, I can partition that in this way, where if I start anywhere in the green interval and I sort of optimize, I roll downhill, I get to the green fixed point. If I take any point in the red interval and go downhill, I get to the red point. Same is true for that yellow interval. They take me to the yellow point. As for the blue points, those are local maxima. If I'm trying to minimize, the only way I end at a local maximum is if I start there. And so basically the stable manifold for each local maximum is just the local maximum itself. That's represented as those 2 x's there. Those are 2 singleton sets. So we've partitioned my feasible region into this collection of points. So the foliation is in fact the union of all of them, right? It's the union of the 3 intervals, green, red, and yellow, and the 2 singleton points, those 2 blue x's. These are called the leaves of the foliation. And so the slide title says, now we can define local inf multiplication. Now that we've talked about what a tame problem is, what an algorithm is, what the stable foliation is with respect to that algorithm, we can revisit that composition law and say, now we can make it make sense in this non-convex setting. So let's go ahead and do that. Our proposed composition law is now this. So we have B1 composed with B2. The composition is parameterized by Y naught. More on that in a moment. And that new composition law we're proposing is this local min over y comma y naught of B1 plus B2. So it's similar to what we had before, straight from Rockefeller, with a couple of critical changes. 1, instead of writing an inf or a min, we now have a local min. 2, we now have this initial condition y naught. That local min operator is defined to be the min over all points y in the leaf that contains y naught. That is a lot of words to express a simple idea. Local inf multiplication is now just inf multiplication over a leaf. If I go back to this previous slide, I said if you start anywhere in that red interval, right, you will roll downhill and end up at the red point. We're capturing that here, right? So if your initial condition is this y naught in gray there, then you are actually optimizing over the red interval. And as we said, you end up at that local min, that y star. So this seems reasonable, but we need to make sure that it actually is, right? This local min operator is not something I've seen someone write out in the optimization context. The stable foliation is not new. That's decades old. I haven't seen anyone do quite this in non-convex optimization. It must be done somewhere. At any rate, I'm confident that this is a useful formalism. It's something I hope to keep using and keep seeing in the future. As for making sure this is reasonable, well, the good news is that this local min map is actually tame. So Previously, I mentioned an optimization algorithm just maps initial conditions to fixed points. It turns out if you take that literally and say your algorithm just maps everything in this stable manifold to the fixed point, that mapping is definable in our O-minimal structure. It's tame. It's something we can work with. That is good news. The bad news is this. If you take what we have at the top of the screen, we'd like to have that diagram, and everything about it looks good except for that why not, right? So the why not doesn't really go there in this categorical context. We don't really get to just throw a point into our composition law when it's used. So instead of doing that, as we get ready to define a category here, we need to figure out what goes in our objects. How do we encode these initial conditions, these why nots that we need? This is the second time I will ask you to pretend you have not seen the slide title. We're working towards a category, but we don't know if we have it yet. To define one, or to hopefully define one, we need objects, morphisms, and a composition law, just like we said earlier. So these objects are now going to be these tuples of 4 elements. So x, n, ax, and x naught. So x is a tame set. You can think of this like a feasible region. N is the dimension of the ambient space that contains X, right? So X may have its own intrinsic dimension. We actually care about the ambient dimension, so we need to sort of annotate our feasible regions with that. That's what N is doing there. A sub X is an algorithm on that set. You can think of this as a vector field adapted to the set X, and then X naught is precisely that initial condition, right? So you can think of this as roughly a pointed set where we've tagged it with the dimension and specified a vector field on it. And then these morphisms are our tame bifunctions, right? So it's the same B as before, the same signature for B, but it's now taken to be tame, definable in our O-minimal structure. And then our composition law uses this local inf multiplication, where if you go down to the bottom of the green box, I've written composition in the same way with that sub why not on the composition operator. That's allowed now because the why not is encoded in these objects. So we can write this composition law. We have the local min like we know we need. And this all looks pretty good. We even get nice commutative diagrams that look like this. And okay, so you do a bunch of analysis. You sort of bang your head against this for a while and you say, yes, we do indeed have a category now. The construction of this category composing all these bifunctions does indeed satisfy all of the category axioms. Which is cause for celebration for a brief moment until we ask the following question. We can say, that is great. Where are the inputs? The letter U is absent from this slide, and that is indeed a problem because in the end, we're trying to model MPC. We need to model optimization of these inputs in addition to everything else that we have. So, okay, hope is not lost. We just need to do a little bit more work. So here's how we're going to do that. We need to incorporate these inputs. Now, these inputs really are external parameters, right? A user applies these. So we need to model somehow extra parameters in our category as well. So here's how we're going to do that. We're going to use a construction. Oh, we have a raised hand. I would be happy to pause for a question.
Yeah.
Hi, Matthew. I want to ask a quick question in terms of why do we want to define a category here? Like, what is it the goal to analyze, say, like the convergence region given an initial points, or yeah, basically like what's the say the next step after defining the category?
I love the question. I love the question. So this is a I'm going to rephrase your question. What's the point of category theory in this? I think that captures the spirit of this. Why use this? It's a great question. I will give a couple of short answers because I have like a 10-minute answer I can give you after the talk. What I will say for now is by abstracting in this way, what we're able to do is potentially weaken the assumptions that we have. So category theory forces you to confront your assumptions, weaken the assumptions that we have, potentially get stronger theorems nearly for free. I'll even add a third reason. More broadly, category theory, right, is a language. Essentially what I'm trying to do here is translate MPC and over time other problems into the language of category theory with the goal of being sort of interoperability. I'll give one example. By having MPC under these very general assumptions in the category theory context, there's recent work from the group of Aaron Ames on defining Lyapunov stability in the setting of category theory. We may be able to get quite general stability theorems in that context as well. So, so far you see me talk about Euclidean spaces. We could define this over lattices and other structures. A lot of the categorical structure remains the same, and it can help guide us as we try to generalize further. Like I said, that's the short version. The long version of that answer is quite long. I think it's a great question. Let me summarize. Generalizing can help simplify our analysis, simplify conditions, and reveal what is really going on. From there, we can extend further. I hope that answer convinces you now. Like I said, afterwards, even if you like that answer, please ask me that again so I can say more. Good. Okay.
Thank you.
Yes, thank you very much. To introduce these inputs, we're going to use para. Para is a construction to parameterize a category that actually comes from that reference in the footnote, developing categorical models of deep learning. We're going to use it in a control context. You can only parameterize certain categories. So for us to do that, we need to define a new category here. All right, so the general rule, you name your categories after your objects if you can. If you can't, you name them after your morphisms. And for us, we have tame bifunctions, so we named our category btame. Btame is this tuple of 3 elements here. So the first element is C. That category from the last slide is part of this. The next is this direct sum looking thing. More on that in a moment. And then the third one is itself a tuple of 4 elements. R0 so R0 is just the origin. That's the feasible region that contains just the origin. It is 0 dimensional. We have the 0 vector field defined on it. That bullet symbol is the vector with 0 elements. Again, that feels a little trivial. Really what's happening with it is we're getting our ducks in a row to define a category appropriately. That direct sum operator does 2 things for us. When it acts on objects, you basically take 2 of those objects, and I'll just say you kind of take the Cartesian product of everything. So you sort of just glue them together in an obvious way. As well, acting on bifunctions, bullet point number 2, you basically just take the sum of the bifunctions, and you have to be careful with how you plug the arguments in, the order in which you plug them in there. None of this is that tricky, right? There's nothing scary, no tricks here, nothing like that. The purpose in doing that is that this lets us define btame. So it's a new category. It is a strict symmetric monoidal category. That is more or less what it sounds like in the sense that it's a category with extra structure. So it satisfies certain coherence conditions, certain isomorphism conditions, other things like that. The point of this is not to dig into the definition. We care about this because it has 2 implications that are really nice for us. So number 1 is we unlock the ability to draw string diagrams. So to illustrate this, we could look at F, G, and H there. So F could be a map from A to B plus C, G is a map from C to D, H is a map from B plus D to E, and then you could draw this you could write this composite here. H is composed of some stuff there's an F in there, right? As a controls person, I am accustomed to drawing diagrams that carry the weight of mathematical rigor behind them. We can do that here. And rather than parsing that weird composition at the bottom, I can draw this picture. And I think it's quite easy to look at that and say, yes, I get what's going on here. So string diagrams are nice, really nice formalism. We're going to keep them with us. The other benefit is, yes, as promised, we can parameterize this category. We're going to do that, and this will help us declare victory over MPC in the categorical context. So to take stock, so far we have made, first we had a category C that didn't have any inputs. And then we made btame, a strict symmetric monoidal category. No inputs yet, but it's getting us there. On this slide, we will define para btame, the parameterized category of tame bifunctions. Here's how this goes. The objects of this are the same tuples as they were before, right? X, N, AX, X naught, same stuff. I'll point out, right there, I'm using this cal X to refer to the whole object. I'm going to keep doing that so so the notation can be kept neat. So rather than, a normal X, if it's the cal X, it refers to the whole object. Okay. With morphisms, a morphism from X to Z is now not just a bifunction, but actually a pair. It is a pairing of an object U with a bifunction F, where F maps us from U plus X to Z. I'm going to come back to this in just a moment It'll make sense in a second. I also just want to say we do have a composition law that looks like this. This composition law down here is kind of formal looking. We don't need to pick it apart. From the definition of morphism and the definition of composition, I want to make good on a promise from earlier. On slide 2, I told you I'd come back to something on slide 13. We're going to do that now. Here's what's being said by that morphism and the composition law. We've basically drawn this. A state goes in and an input goes into F1. A new state comes out of that. Then another input V comes in and another state Z comes out. Speaking in very rough, loose, intuitive terms, what we've captured was precisely that humble observation from earlier, right? Given a state, if I specify my next 2 inputs, I can move your state forward in time by 2 time steps. I can take you from xk to xk plus 2 by applying the input u and then applying the input v, right? So really the point of this category is it implies this, what's on the bottom of the slide. It has captured how we know our control systems ought to look, how they ought to work, right? So this says we are on a good path. We've parameterized our category. We've incorporated inputs correctly. So now we're going to write out MPC problems in this context. We're going to start with the simplest possible MPC problem, and then this will tell us that harder problems aren't too much harder. So we're going to look at a one-step MPC problem here, right? So I'm just optimizing my cost right now. If it's time k, that's L of xk comma uk. I'm minimizing over my current input, and it's subject to, I've got my dynamics, I've got my inequality constraints. Associated with this problem is this one-step bifunction G. The full signature of G is there, but really G takes in an input object plus a state object, and it equals what's on the right. So we'll go from right to left. I've got my constraints and my dynamics with these indicator functions. So if you're obeying all your inequality constraints and you're obeying your dynamics, then those indicators output 0. And then G is just equal to whatever your cost is. If you're infeasible, you're infinity. So it's a bifunction just like we had before, but now we've got inputs in there. And it turns out that this one-step MPC problem is precisely a morphism in this category. It's a morphism in the para-B-tame category. And a morphism in this category is a pair U comma G, right? So it's an input object alongside a tame bifunction G. This one has a string diagram as well. Pictorially, it looks like this. Again, roughly speaking, a state and an input come in and a new state comes out. So that's a one-step bifunction. One-step bifunction gives a one-step MPC problem. To do full MPC, we're basically just going to line up a whole bunch of these. We can make that precise here. So here's what we're going to do, right? This is the full thing now. We will consider this full n-step MPC problem. We're minimizing my cost summed from now to a certain number of time steps in the future. Got my dynamics, got my inequality constraints. All the pieces are here. And then what we will do is we will let this ui comma g be the morphism that corresponds to time I, right? So essentially what we're saying is over my whole time horizon, associated with each time, I have a one-step bifunction for that time. Good. This right here is how you define MPC in a categorical context. An n-step MPC problem is just a composition of these n morphisms. So it's ut with g, the input at time t with g composed with the next one, time t plus 1 with g, on and on and on and on through the end of the time horizon. As promised, you form this basically by lining up all the pictures, right? So you can think of a state coming in now, all my inputs coming in at each time, producing some state at the end of the time horizon. So we've gotten here to this model of MPC in the context of category theory. I was actually planning on saying a little bit here at the end, just a very brief spiel about the role of category theory, I think, going forward in autonomy. And I greatly appreciate the question earlier that even planted a seed for this. Let me reiterate a few points and maybe add some new ones. So category theory is a language. It's something like a universal language. I was joking once that category theory is a universal language for everyone, but it's like we're asking everyone to learn Esperanto, right? Where it is a challenge and it is a big ask ultimately. It's something I myself have been working on for a few years now, basically since I met James Fairbanks. He has got me into this, as have a few others over time. Category theory offers the ability to put what we do into a common language. It offers the ability, let me rephrase that, it forces you to confront what your assumptions are. Non-convex optimization is something I've thought a lot about. In the course of this project, we learned a lot about what is going on under the hood, how to model that, how to frame that, how to think about that. From there, we gain the ability to generalize, right? So this is MPC and state space systems. On the first slide, I had things like Markov decision processes, repeated games, other systems. Those are all on the horizon for us. I think we can get those into a shared framework, identify common threads, maybe use common analyses across all of them. So that's sort of a very large, big research plan, but something I'm excited to be a part of, look forward to contributing to. I'll go ahead and stop there. Happy to take more questions. My name is Matt Hale. I'm from Georgia Tech. Thank you very much for listening.
Thank you, Matt. This was a great talk. So let's see, let's open the stage for questions. People, you can write in the chat, you can raise your hand. I think we already have
We have a raised hand, yes.
Okay, hello. Hello.
Hey.
Yeah, it's a great talk and I have many questions indeed, but I'm gonna ask one hopefully quick one that should be easy. So I see that in the definition of this category, the optimization algorithm and the initial points are integrated into the objects.
Yes.
Are you guaranteed that when composing with each other in this way, these algorithms will behave the same as they are run individually?
Okay. Yes, I love the question. Okay, the direct literal answer to your question is no, you're not guaranteed that. The real answer is, well, you are. So basically the category gives you enough flexibility to do this badly, right? That's all sort of in there. The category is rich enough to contain the ability to do bad things. And something like MPC, though, you retain the guarantees that the algorithms do the correct thing. So I guess what I'm saying is that is not guaranteed by the structure of the category. It is guaranteed by putting this to use by modeling sort of any reasonable thing, if that makes sense.
Okay. But I'm saying, so for instance, in the category, you also have to incorporate the definition of these, how do you call it, the convergence regions.
Yeah, yes.
In the definition of the category, you have to guarantee that when you compose these algorithms with each other, these convergence regions does not change. Otherwise, the definition of the category does not make sense. Is that correct?
Okay, so I think I understand the question better now. Essentially, what is the right way to say this? You can think of it as within each object, the algorithm has been specified. My composition law does not alter the algorithms in some strange way. It preserves the structure of them as I compose. I would have to dig into the math to show that, but you do not lose that structure.
Okay. Okay, I kind of see it. Okay, thank you.
Yes. Yes. And by the way, for you and everyone else, please tell me if I'm answering the wrong question, right? If I've misinterpreted you, please tell me that. I'll try again.
No, it's perfect. Okay.
Thank you.
Eugene, did you have another question, or is anybody else? Does anybody else have a question?
Hi, Chaoji here from UB. Can you hear me?
Oh, hey, Chaoji.
Hi. Thank you very much. Very nice talk. I get used to this category theory, or get introduced to this at ACC this year, and I was browsing Ames paper on the Lyapunov theory on this
Wonderful
category theory. That was very fascinating, and thank you for this nice introduction to me at least. So I as a practitioner, I sort of have this question from a user perspective. I know this is a general language that we can speak, other people can understand, but does this actually help, for example, for us to make sure the MPC is more solvable? We actually can make it recursively feasible, it's safer, or maybe solving it even faster. So does that category theory actually can help or lead to that?
Yeah, love the question. Very quick. When you said you were at ACC, were you at the workshop that this group of us?
Yes, I was at the workshop, yes, but I came in late, so I only listened to the later part due to flight delay.
Oh, no, I think it's great that you were there. Thank you very much for attending. You spread the word. So, okay. Yes, your question, I think, is basically, if I understand it, how does this help the bench engineer? Is that yes? So, oh God, what a great question. Let me offer a short answer and a long answer. The short answer is this use of category theory can do a few things. One is automatic generation of correct by construction software, and two is essentially error checking. It can tell you if there's certain types of errors in there. Category theory is good at helping find that. There are other ways to do those things, but category theory offers nice automated tools for that. The longer answer I would say is category theory offers a depth of understanding about a problem. I realize that's sort of vague and unsatisfying, but I mean, in the end, I would say understanding what's going on under the hood for someone willing to dig into this, that is part of the payoff for this as well. But for someone who is out in the wild solving problems, I would say you can do things like draw pictures, draw a string diagram, and get provably correct by construction software without having to write any code yourself. You can also do things like, yes, in your implementation, identify that it is ill-specified in some subtle way. You can get detection of that through the use of category theory. So it's maybe not for every bench engineer, but I do think there are benefits here.
Thank you. I think that the short answer particularly was very helpful. Basically, I understand that this could potentially lead to an automatization of software synthesized safety verification for a very general class, as long as we put it into this category theory.
Exactly. And so we have not built out that capability yet. My
Right.
collaborator, James Fairbanks, who I mentioned a couple of times, that is one thing he's quite adept at, and it's something on the horizon for us for sure.
Sounds good. Thank you very much.
Thank you.
Thank you, Jose. Any other question?
So maybe I can ask another one.
Yes.
Yes, please do.
Yes. Okay. So another thing is summation a critical part of this storyline? Like summation in the infinitum definition at the very beginning. If we replace it by, say, minimum or infinitum, like summation of these b functions.
I think you mean here?
Yes. You take infinite over y of the summation of b1 and b2.
Yes.
Is this a critical choice in this framework, or I can replace it with any, say, monotone functions from whatever to whatever?
Does it even have to be monotone? I think it's kind of associative, no? Maybe it's an associative operation.
Yes, yes. So here we're after associativity. What you're asking is an interesting question. I have not thought about it, but let me tell you what my gut reaction is. My gut reaction is that you can replace the operation here. Summation happens to work very well because it helps us encode things like MPC problems. It's easy to believe there are problems that cannot be encoded in this way, in which case defining a different composition operation may be the way to go. Some other, monotonicity I think would be nice, but maybe is not even strictly required. I haven't thought about that. That's intriguing though. I will say we saw this in Rockefeller and we said, oh, good, we can use that and built this on top of it. It's certainly interesting to revisit those foundations. That could lead to a million things. That's a great question.
Yeah, actually, even in MPC scheme, there are cases of infusing stage-wise costs other than summation, right? So it might be something.
Yes, let me also add to that. We have the ability to impose additional constraints, like you can impose periodicity constraints and things like that. I didn't present that because it gets in the weeds, and I didn't want to go over time. But we have the ability to incorporate other constraints like that as well. So I mean, what you're getting at is something I'm very interested in, which is how do you build out these other capabilities from here? We want this to be kind of a fully fledged framework for this. So yeah, do you have another class of constraint that is maybe most interesting to you? Or cost for that matter?
Well, I'm thinking about the general way of composing two optimization problems, like I'm just reasoning out loud.
Yes.
So for instance, in code design, we kind of replace the summation with an AND operator and the infinitum with a union operator or an OR operator. So I don't know, maybe That's one example of replacing the summation and infimum operator with another operator.
Yes.
And there
yes.
might be other in other application domains.
Yeah. So one thing that I said in the talk that I should have repeated sooner just now is that what you capture with the summation here is the idea that my decision now parameterizes my constraints at the next time, right? So taking the sum, doing this inf multiplication, captures that notion. And so what you're describing, I suppose, changing this composition operator, seemingly the motivation would be there is a different relationship between a decision now and what happens at the next time. So perhaps if you are non-linearly parameterizing your constraints, right? So on this slide in the upper right with y1 and y2, these are parameterized, we've parameterized the constraints in a certain way. You could think of g of x comma y1 less than or equal to 0, for example. I'm not even sure what that would represent, but then you would need a different composition law because a decision now does something else at the next time, right?
Okay, that's great.
Yes. It sounds like you work on category theory.
Oh yeah, Eugene
Yes.
is my PhD student.
Oh, that explains a lot. Okay.
And actually will be, I think if we have some of these questions, those could be nice overlaps we explore in our joint grant and efforts.
Yes, absolutely. Yeah.
Yeah, Eugene is my compositional student. One of my
Okay.
compositional students.
Yes, well, good. Yes, you all have met Hans, who is my resident category theorist.
Yes.
In the event that both of you will be in Rio, we could actually sit and really hack some of this out for CD.
Exactly.
That's great.
Exactly.
Yeah, that'd be good. Looking forward to it. Yes, but Eugene, I hope I have sufficiently answered your questions for now. If I have not, tell me that and I'll try again.
No, it's fantastic. Thank you.
Wonderful. Thanks.
Thanks so much, Matt. I think we are at time, but the talk was amazing. I have a lot of ideas. We should indeed, in Brazil, we should get down to the whiteboard and discuss some ideas. But thanks again for coming. I'll reach out when I have the recording, but I look forward to talking again soon.
Yeah, thanks very much for the invite. I do know that in 2025, it's easier than ever to talk with people from a distance, and yet I have to go to a conference to actually establish these collaborations. So anyway, if nothing else, we will absolutely talk in Rio. Looking forward to it. Thanks very much for the invite. This was great.
Thanks so much again. Bye-bye. Take care.
Bye. Take care.